This is AS Chemistry Lesson 1 on enthalpy changes. So we'll start by looking at a few definitions. Certainly this topic on energetics will have a lot of definitions you will need to learn for the exam. So it's crucial you make a note of the definitions and you highlight keywords that you will be certainly marked on. So the first definition we're going to look at is of enthalpy change. So enthalpy change, delta H for a reaction, is the change in heat energy at constant pressure. So the definition of enthalpy change, which has the symbol delta, which is the triangle H. So the enthalpy change for a reaction is the change in heat energy at constant pressure. And usually that definition is worth 1 mark in the exam. And although it doesn't come up frequently, it is one worth certainly remembering. Moving on to looking at the standard enthalpy change. Now, when we look at the symbol for the standard enthalpy change, we can see that it's different to the enthalpy change. It's got a little planet Saturn sign, a little superscript, little planet Saturn sign. That's a circle with a line going through it. And I'll talk you through what that means in a minute. So the symbol for the standard enthalpy change is delta, again the triangle with a H with a little superscript with a little planet Saturn sign. That's what I'm going to call it. So the standard enthalpy change is the change in enthalpy under standard conditions. And standard conditions are 100 kilopascals and 298 Kelvin, with all substances in their standard states. So I'll say it again. The standard enthalpy change, delta H, is the change in enthalpy under standard conditions, 100 kilopascals, 298 Kelvin, with all substances in their standard states. Now, whenever you do write standard conditions in the exam, always state what the standard conditions actually are. And that's 100 kilopascals and 298 Kelvin. And again, I've underlined keywords such as standard conditions and standard states. And that's very, very important. We'll talk more about what we mean by standard states later on, but the standard state is just referring to the state of matter, so solid, liquid, or gas. Okay, and that's what we're saying. So the substance you're looking at, for instance, if I was looking at methane, which I know is a gas, then the standard state of methane would have to be in brackets with a G. I wouldn't expect to get a liquid methane, for example. Okay, but that's what we're looking at. We'll learn more about that as we look through examples. The standard enthalpy change has units of kilojoule per mole, and the little planet Saturn sign, as I've pointed out, what it indicates to you is it indicates that the substances are in their standard states and that the conditions used are standard conditions, which are 100 kilopascals and 298 Kelvin. So if you've got that symbol, then you know that the conditions that they're referring to are 100 kilopascals and 298 Kelvin in the exam question. So make sure you learn these definitions for the exam, write them down, highlight the keywords like I've done, and keep repeating them to yourself until you learn them, because they are likely to come up in the examination. And there's a lot more to learn in the energetics topic. Okay, moving on. So reactions, and certainly this is something I hope you've seen at GCSE, can be exothermic or endothermic. And exothermic means that heat energy is given out, and endothermic means that heat energy is taken in. So exo, giving out heat energy, and endothermic is taking in heat energy. And you might also remember from GCSE that an exothermic reaction has a negative enthalpy change, and an endothermic reaction has a positive enthalpy change. So exothermic reactions give out heat energy, and delta H, which is the enthalpy change, is always negative. And endothermic reactions take in heat energy, and delta H, which is the enthalpy change, is always positive. You also need to know for the exam how to draw reaction profiles. And this is something you may have seen or you may have not seen. And what I'm going to show you is what the reaction profiles look like, and I'm going to talk you through each of these so you understand what they are. So these are sometimes referred to as reaction profiles, Sometimes they'll just ask you to just draw some lines on a graph to show you the energy of the reactants and the products. And I'm going to talk you through this reaction profile for an exothermic reaction. And again, you may have seen this at GCSE. So whenever you draw a reaction profile for an exothermic reaction, and then we'll look at endothermic reaction in a minute, what you start by doing is you start by drawing two axes. So an X and a Y axis. The Y axis is labeled energy, just like I've done on this picture here. And the bottom part, you don't really need to put a label, but it's useful just to write progress of reaction. You then start by drawing two horizontal lines, one for the reactants and one for the products. So that's the line that's drawn in green and blue, but when you're drawing it in the exam, you just draw it using a pencil, two lines that are the same. Now, in an exothermic reaction, this is the rule, and this is crucial to remember. The products are always lower in energy than the reactants. Okay, so I'll say it again. In an exothermic reaction, the products are lower in energy than the reactants. So therefore, the line for the products will be a lot lower than the line for the reactants. And that's why the blue line is lower than the green line, because it shows you that the products are lower in energy than the reactants. So when you draw this, draw your axes, draw a reactant line and a product line. A line for the products, a horizontal line which is lower than the line for the reactants. And label it reactants and products, like the green and the blue lines. And then you need to draw this hump. And I always call it this hump that we've got. And that's a line, a hump that you've got from the reactants going all the way down to the products. So that's like a camel's hump. So from the reactants going to the products. So reactants are high in energy, over this hump, go down up to the products which are lower in energy. And that's your exothermic reaction profile. That's what they're interested in. But there's a few more labels that we can add other than reactants and products. And that's this line which we've got there, which is labeled EA, or the arrow labeled EA. And that's the activation energy. So shorthand notation for the activation energy is EA. That's capital E with a subscript A. And that's the activation energy. And the activation energy is the minimum energy required for a reaction to occur. Without that energy, the reaction will not take place. Okay, so that's what the activation energy is. Now, in a reaction profile, to work out where the activation energy is, it's always from the reactants to the top of the hump. That's how you know where the activation energy is. So from the reactant line to the top of the hump. And you can see clearly in this picture, they've just extended the reactant line and drawn an arrow from the reactant line to the top of the hump and labeled it EA. And that's the activation energy. That's the minimum energy required for the reaction to occur. The energy change in this reaction is the difference in energy between the reactants and the products. And the difference in energy between the reactants and the products is the enthalpy change, which is delta H. And in this case, they've drawn a line between the reactants and the products. So again, extended the reactant line and draw a line between the reactants and the products. And the difference in energy between the reactants and the products is called the enthalpy change, delta H. And delta H in an exothermic reaction will always be negative. And when we do calculations, we'll certainly see that. So remember, that's the shape of the exothermic reaction profile. Products are lower in energy than the reactants, so you draw two lines, one for the reactant, one for the products. The products are lower in energy than the reactants. You label them reactants and products. You then connect the two horizontal lines with a big hump, okay, and you label the activation energy, which is the minimum energy required for a reaction to take place, and that's from the reactants to the top of the hump. And you label the enthalpy change, delta H, which is the difference in energy between the reactants and the products, clearly on your diagram. Okay, let's move on and let's look at the endothermic reaction profile. So again, the axes are exactly the same. You've got the y-axis with energy and the x-axis with progress of reaction. The difference between an endo and an exothermic reaction is that the products are higher in energy than the reactants in an endothermic reaction. So when you draw an endothermic reaction, okay, remember the products will always be higher in energy than the reactants. So to reflect this, the line for the products must be higher than the line for the reactants. So again, when drawing this, you draw two horizontal lines, one for the reactant, one for the products. But this time you draw the line for the products higher than the line for the reactants. Okay, so you draw a line for the reactants, which is in this case the green line. You draw a line for the product, which is higher in energy than the reactants, which is the blue line. And again, you connect it up via this hump, just like we were doing before. So two lines, reactants and products, clearly label them, and then a hump between the two. You then need to label on the activation energy and the enthalpy change. And just like before, the activation energy is the minimum energy required for a reaction to take place. And this time the activation energy again is not just like before, it's from the reactant line, which they've just extended on this picture. Look at the orange line, which is labeled with EA. So from the reactants to the top of the hump. Okay, so from the reactant to the top of the hump, that's the activation energy for the reaction. The enthalpy change, remember, is the difference in energy between the reactants and the products. So it's just from the reactant line, which we've extended, and showing the energy difference between the reactants and the products, and that's labeled as delta H, which you can see on this picture. And delta H in an endothermic reaction is always positive. So two things to note here. In an endothermic reaction, the products are higher in energy than the reactants, and that the enthalpy change is always positive. Another thing that's important is that in an endothermic reaction, it's a reaction which takes in heat energy. And we can clearly see that in this case with the endothermic reaction, it's got quite a high activation energy. And it makes sense that you actually have to put in a lot of heat in order for this reaction to take place, because it's got a very high activation energy. And that's reflected in this curve, which is called a reaction profile. So make sure you can draw these out on a piece of paper confidently, and you can label the activation energy and the enthalpy change at delta H, because they will ask you to do this in the exam. Okay, let's move on to another term, and this term is called the enthalpy of formation. And throughout the lessons, we'll certainly be referring to the enthalpy of formation quite a bit. The definition, which looks scary at first, is not too difficult to learn. Now, I'm going to start by just talking about the symbol for the enthalpy of formation, and then I'll go through the definition followed by an equation. The symbol for the enthalpy of formation is delta H, where the little planet Saturn site, and a little F, and the F means it's the enthalpy of formation. But more recently, sometimes in exams, they've slightly moved things around, and they've put delta, they've put the little F, a H, and then the little planet Saturn sign next to it. So regardless it's delta H with a little planet sign F, or whether it's delta F H with a little planet sign, it makes no difference. It is still the enthalpy of formation. So the definition for the enthalpy of formation is the following. The standard enthalpy of formation is the enthalpy change, that's crucial, when 1 mole of a compound, that's your first mark, when 1 mole of a compound is formed from its elements, that's your second mark, so formed from its elements in their standard states under standard conditions, and that's your third mark. So this definition is worth 3 marks. The standard enthalpy of formation is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states under standard conditions, and it's worth 3 marks. The marking points are 1 mole of a compound, that 1 mole is crucial. Second mark is by saying formed from its elements, that elements word is absolutely crucial, and then saying in their standard states under standard conditions. So we're looking for those words in their standard states under standard conditions for your third and final mark. So make sure you write this down and you keep practicing this definition. Now let's look at an equation to represent the standard enthalpy of formation of water. So as the name suggests, standard enthalpy of formation, you're making something, okay? And as the definition says, let's see if you can apply the definition and to writing an equation. We're interested in making 1 mole of a compound. It's going to be formed from its elements, and the elements are going to be in their standard states. That's the 3 things we're really after when we're writing one of these equations down. Now, if you want to on a piece of paper, try to write down the equation for the standard enthalpy of formation of water and see what you get to. So I'm going to start to go through it, and you might choose to pause it if you want to have a go yourself. Water, we know, is H2O. So the formula of water is H2O. We know that the elements that make water are oxygen and hydrogen. And both oxygen and hydrogen are diatomic, i.e. they exist in pairs. So it's going to be O2 and H2. So on a piece of paper, you could write down H2 plus O2 gives me H2O. And the problem is the equation is not balanced. And straight away what people will do is they will start to balance the equation by saying, well, H2 plus O2 gives me H2O. 2 oxygens on the left, 1 oxygen on the right. Let me put a 2 in front of the H2O. So you've now got 2 H2O, and then the hydrogens don't balance, so I'll put a 2 in front of that. So they end up writing 2H2 plus O2 gives you 2H2O. Now, even if we put state symbols in, the answer is still wrong. And the reason it's wrong is because by putting a 2 in front of water, you've automatically lost your mark. The definition says you're only forming 1 mole of a compound, and therefore you must reflect this in your equation. So you must never put a 2 in front of the compound, even if it means that you need it to balance it. Instead, you must use halves or fractions if you need to, but there must be a 1 in front of the compound that you're forming. So in this case, what I've done to balance it, so H2 plus O2 gives me H2O, is because there's 1 oxygen on the right and there were 2 before. I had to put the half there on the left. I know half of 2 gives me 1, so I've put a half in front of the oxygen to balance it. So H2 plus half O2 gives me H2O. And I've put state symbols, and remember the elements are in their standard states. So elements are hydrogen, which is always a gas, oxygen's a gas, and they're the elements in their standard states. And water, as I know, is a liquid, in this case liquid water. So key things: 1 mole of a compound has been I've got 1 mole of a compound. I've got it's formed from its elements, so water is formed from hydrogen and oxygen. I've included that, and I've also put their standard states, which is crucial. So when writing an equation to represent the enthalpy of formation of a compound, make sure you take those 3 points into consideration. 1 mole formed from its elements, and they're in their standard states. The enthalpy of formation of water is minus 285.5 kilojoule per mole. You don't need to memorize that for the exam. All that tells me it's an exothermic reaction because it's got a negative enthalpy change, and that's it. So there it is, 1 mole of water. All substances are in their standard states, and that's the reaction profile. It's an exothermic reaction because it's got a negative sign. Okay, moving on to another definition, and this one again, just like the enthalpy of formation, is very, very big as well. But you have to learn these 2 for the exam, and they have frequently appeared in the exam paper. So make sure you learn them, and they're worth 3 marks each. The symbol for the enthalpy of formation was delta H with the planet Saturn sign F. The symbol for the enthalpy of combustion is delta H planet Saturn sign C. So the F is being replaced by C to reflect the enthalpy of combustion. So let's go through the definition. The standard enthalpy of combustion is the enthalpy change where 1 mole of a compound is completely burned in oxygen under standard conditions, and all substances are in standard states. So I'll say it again, the standard enthalpy of combustion is the enthalpy change where 1 mole of compound is completely burned in oxygen under standard conditions, and all substances are in their standard states. Again, key marking points are 1 mole of a compound, that's crucial. And then you have to write completely burned in oxygen. That's absolutely crucial that you write that, completely burned in oxygen. That's your second mark. And then standard conditions, and all substances are in their standard states. And that's very, very important. So 1 mole of a compound, completely burned in oxygen, under standard conditions, with all substances in their standard states for the third and final mark. So learn that for the exam. And again, just like before, we always include an equation just to reflect this process. So we're going to look at the combustion of ethane. You should be able to write an equation to represent the enthalpy of combustion of ethane. Now, because it says it's completely burnt in oxygen, that means that complete combustion is taking place, and that's producing carbon dioxide and water. Okay, and that's crucial to remember. So try and write an equation on a piece of paper and see if you can balance it. Okay, there is my equation here. Okay, C2H6 plus O2 gives me CO2 plus H2O. And then I've balanced the carbons on the left, so 2 carbons on the left, but I'm putting a 2 in front of the CO2 on the right. I've balanced the hydrogens, so there were 6 on the left. There were initially 2 just in water. I've put a 3 in front to get 3 times 2 to 6. And then if you count the oxygens, you've got 4 in carbon dioxide, 3 in water. 4 and 3 gives you 7, and 3.5 times 2 on the left will give you 7. So that's my balanced symbol equation. And again, sometimes, and I've said this when we looked at writing combustion equations, I pointed out I don't like having half an oxygen. You could double it to get rid of the half. So you could put 2C2H6, 7O2 goes to 4CO2 and 6H2O. But unfortunately, you wouldn't get your marks in the exam. And the reason you wouldn't get your marks in the exam is because it says 1 mole of a compound is completely burnt in oxygen. So be careful. If it means you have to include a fraction, you do, because you're only burning 1 mole of a compound, and that's crucial. So don't double it and put a 2 in front of the compound. So again, key things we're looking for: 1 mole of compound, it's burnt in, not completely burnt in oxygen, so the products of carbon dioxide and water, and we're putting the substances in their standard states. So ethane is a gas, oxygen is a gas, carbon dioxide is a gas, and water is a liquid. The enthalpy of combustion for combusting ethane is minus 1560 kilojoule per mole. That number you don't need to memorize for the exam, it just tells you it's an exothermic process. Now, any combustion reaction, whenever you burn any substance in oxygen, it will give out heat energy. So all combustion reactions will be exothermic. So complete combustion produces carbon dioxide and water. Okay, moving on. Now it's a task for something for you to try, because we've looked at several definitions, which I'm hoping you've either written on a piece of paper or you will go back through this lesson and remember, because those definitions are crucial and they come up in the exam. Hopefully you understand how I've generated the enthalpy of formation and combustion equations by looking at the definition, and they do apply to the definition as well. What I want you to do is to see if you can write some as well yourself. Okay, I've got 3 on this slide. 1 for the enthalpy of formation of methane, that's the first one. The second one is the enthalpy of formation of ammonia, which is quite popular in exams. And the final one is the enthalpy of combustion of butane. See if you can write equations for them, making sure you look carefully at the definition in terms of the number of moles, looking at, make sure the equation is balanced, making sure that it's formed from, say, its elements, if it's enthalpy of formation. Make sure that you are including the state symbols to represent the standard states, and try this on a piece of paper. What I'm going to do is to go through the answers now, so you might wish to pause the presentation at this point. So let's look at the first one, which is the enthalpy of formation of methane. We know that the product is going to be methane CH4. The elements which form it are carbon and hydrogen. Carbon is C and hydrogen is H2. And then we proceed with balancing the equation. So carbon plus hydrogen, which is H2, gives me methane, which is CH4. And because we've got 4 hydrogens on the right, and initially we had 2 hydrogens on the left, we put a 2 in front of the hydrogen, so that's where the 2H2 comes from to balance the 4 hydrogens on the right. We then include state symbols, so we put solid for carbon, because carbon's standard state is a solid. Hydrogen's a gas and methane's a gas, and that will give me my marks in the exam. Key things to check once you've written it is it 1 mole of a compound? Yes, it is 1 mole of a compound, 1 mole of methane. Is it formed from its elements? Because that's what enthalpy of formation is. Yes, it is, carbon and hydrogen. And are they in their standard states? Well, everything is in its standard states. Carbon is a solid and hydrogen's a gas, and we know that methane is a gas as well, and that will give me my marks in the exam. The next example, which is the enthalpy of formation of ammonia NH3, is a bit more complicated. Ammonia NH3 is our product, and it's formed from the elements nitrogen and hydrogen. And nitrogen and hydrogen are diatomic, so nitrogen is N2 and hydrogen is H2 as well. Again, the most popular mistake in exams is that a lot of students will start to balance it straight away and say 2 nitrogens. Since nitrogen is N2 on the left, we're going to put 2 in front of NH3, and straight away they've lost their mark because enthalpy of formation is only 1 mole of a compound. So when we write this equation, N2 plus H2 gives me NH3. The one thing you must remember is not to put a 2 in front of NH3, because that becomes 2 moles of ammonia, and you're not interested in 2 moles because the enthalpy of formation is forming 1 mole of compound from its elements in their standard states under standard conditions. So don't change that. So I've got 1 mole of ammonia, and then balance the equation. So I don't want 2 nitrogens, I want 1, so we put a half to reflect that. Half times 2 will give me 1. And in terms of hydrogens, we want 3, so 1.5 or 1.5 times 2 will give me 3, and that's where that comes from. And then we put the standard state. So nitrogen's a gas, hydrogen's a gas, and ammonia is a gas as well. So make sure you write it correct. The final example is the enthalpy of combustion of butane, C4H10. Enthalpy combustion, again, is where 1 mole of compound is completely burnt in oxygen. So products are going to be carbon dioxide and water, is what we're looking at. So there it is. There's the equation. C4H10 plus O2 goes to CO2 plus H2O. 4 carbons on the left. Put a 4 in front of CO2 to balance the carbons. 10 hydrogens on the left. Again, 5 in front of water. 5 times 2 will give you 10. So that's balancing the hydrogens. And then if you count the oxygens on the right hand side, you'll see that there are 8 in carbon dioxide, 4 times 2, and 5 in water, which gives you 13. And 6.5 times 2 from the oxygen will give you 13. And again, it's 1 mole of a compound that we're completely burning in oxygen, and we're putting the substances in their standard states, which is important. So gas, 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 and liquid. So make sure you can do that and write that for the exam, because they will expect you to do this. This concludes the lesson on enthalpy changes. Lesson 2 will look at calculating enthalpy changes.